Now that we have actually derived the chain rule, we can actually use it to restate some of our other rules in a slightly more general form. Let's take our power rule. So remember the derivative of x to the n, we bring down that n in front, and reduce the power by 1. What we can do here is we can replace x with a function. We'll say we have a function u of x that we're going to put into it, and we'll differentiate that u to the nth power. Notice here that we are not differentiating with respect to u, so even though we're not really expressing this as a function of x, we still are thinking of it as a function of x. And we're going to follow the same rule, so we'll still have n times u to the n minus 1, but now the chain rule also tells us we need to multiply by the derivative of the inside function. The inside function here just being u. So the derivative of u to the n with respect to x, not with respect to u, is nu to the n minus 1 times the derivative of u. This is what is sometimes called the general power rule. And in fact, some of your homework problems will probably ask you to use the general power rule in order to do some problems. Really, we're just using the chain rule and using the regular power rule, but here it's just kind of combined. Now, this is a pretty common thing to do. If you look at tables of derivatives, a lot of times they're stated in this same kind of way. In fact, if you have a physical copy of the book, you should open it up to the just inside the back cover. There's a table of basic differentiation rules that's on the top left. And if you don't have a copy of the book or don't want to dig your copy out from wherever it is, here it is right here in front of you. These are all summarized in the back of the book. One thing to keep in mind here is that we're always differentiating with respect to x. All these are ddx, not ddu. The u's and the v's that are in here, these are all being treated as functions of x, and we want to keep thinking of them as such. But notice here that all of our basic rules are here. I guess the chain rule isn't really written down here by itself, but it's kind of incorporated into all the other rules. So 1 is just our multiple rule, 2 is our addition and subtraction rules, 3 is the product rule, 4 is the quotient rule, 6 is our general power rule that we just stated up here. In fact, you can see exactly what same kind of form that we have there. 5 and 7 are just specific examples. This is just saying that the derivative constant is 0. This is saying that the derivative of x by itself is 1. And you can even see some rules that we haven't even gotten to yet. We haven't talked about logarithms or exponentials yet, but the rules are summarized there anyways. And we're not even going to talk about the trig functions, these 6 down here at the bottom. But this is a nice thing to remember whenever you're kind of having trouble remembering a rule or something. The point here, though, is that these formulas are written with the chain rule already in mind. So here, like this is the logarithm, but when we're differentiating the logarithm, they're putting a u here, a function of x, instead of just putting ln of x. And so the derivative of u is incorporated into the formula. Same thing with e to the u. If this was e to the x, we wouldn't need the derivative of u in there. But that's pretty much the general way a lot of tables of differentiation rules are presented. They're presented with the chain rule already in mind. But we're just more interested in just applying the general power rule, because we don't have natural logarithm or the exponential function quite yet. We won't be talking about those for actually a couple chapters. It should be chapter 4, I believe. But let's just keep working some problems. Let's do problem 22. Here we have a function f of x is equal to 2x cubed minus 6x to the 4/3 power. And so note here we have a function to a power, the power here being the 4/3 power. We can think of this either as a composition of u equals 2x cubed minus 6x and y is equal to u to the 4/3. We can treat it that way and use the chain rule, or we can just skip right ahead to use the general power rule. And that's what I'm going to do here. The general power rule says that if we have some function to this power, we bring down that power out in front. We reduce the power by 1. So 4/3 minus 1, you have to work out what that is. That's actually just a 1/3. And then we need to multiply by the derivative of what's inside the power. The derivative of 2x cubed minus 6x. Well, here the derivative of x cubed is 3x squared. Combine that with the 2, we get a 6x squared. Derivative of 6x is just 6. So we have minus 6. We follow this up with problem 30. This one's actually fairly similar, except it's not going to look as similar. We have y is equal to 1 over the cube root of 4 minus x cubed, all to the 4th power. Now that doesn't really look similar to what we had up there, but the key to working out this problem is to recognize that we are just looking at a function to some power. Note that the cube root is really a 1/3 power. Combining that with the 4 that we have here, we're really taking the 4/3 power of this 4 minus x cubed. But being on the bottom of this fraction means that our power is really negative. So if we write this out in a few different steps, maybe the way we might think about it is that the cube root of this to the 4th power is that stuff to the 4/3 power, and then that 1 over that means that we have 4 minus x cubed to the negative 4/3 power. And now it actually looks very similar to what we have up there. Just we have a negative power instead of a positive power, and a slightly different function inside of there. And so we're going to do exactly the same thing. Differentiate with this using the general power rule. So with the general power rule, we're going to take this power out in front, this negative 4/3 out in front. We're going to keep what we already had inside, but our new power, we're going to take the negative 4/3 and we're going to subtract 1 from that. This time, instead of becoming a 1/3 or negative 1/3, it actually turns into a negative 7/3. Negative 4/3 minus 1 is negative 7/3. And now we need to multiply by what's inside, the derivative of what's inside there. Derivative of 4 is 0. Derivative of x cubed is a 3x squared. Of course, we still have the minus in front of that x cubed, so that'll be a minus 3x squared. And maybe at this point we'd want to go ahead and put it back in terms of cube roots and fractions and all that like we had originally. If we do that, well, we have the negatives cancel out. The 3's actually cancel out. So we'll have a 4 and an x squared. For this part in here, remember the minus sign means it's on the bottom. So we'll have the 4x squared on top. But we'll have this 4 minus x cubed. This will be to the 7/3 on bottom. Maybe I'll go ahead and write this out in multiple steps. Of course, the 1/3 in this exponent means that we're going to have a cube root. So 4x squared over the cube root of 4 minus x cubed. But now it's to the 7th power instead of the 4th power that we had before. I mean, technically, those are all different forms of the same derivative. Whichever one you really prefer is up to you. I would probably actually I like this one a little bit better. I don't always like to have the roots and powers kind of mixed together. I'd rather just leave that as a fractional power. For our last example, let's look at the function f of x equals x plus 1 over the square root of 2x minus 3. This is problem 63, and the directions here are a little bit different than what we've been seeing in some of the other ones. We're not just asking for the derivative of this function. Instead, they want the tangent line at the point 2, 3. We want the equation of the tangent line. In order to do this, we're going to have to muster all of the stuff that we have learned about differentiation to solve the question. Well, first of all, note that finding the tangent line does require us to have a slope. We have a single point, and we need a slope to go along with that. And that's what our derivative does for us. It gives us the slope of our tangent lines. So we're going to have to differentiate this function. It's also a quotient, so in order to differentiate it, we're going to use the quotient rule. That's our first step. We're going to use the quotient rule. I'm going to go ahead and label these just to keep track of where we're at, but you don't have to do that in general. So our quotient rule, we're going to take the derivative of the top, derivative of x plus 1. Well, that one's pretty easy. That's just a 1. Times the bottom. The bottom is our square root of 2x minus square root of 2x minus 3. Getting all tongue-tied there. But for the moment, we're just leaving that as it is. Now we're going to leave the top as it is. We're subtracting. Remember the subtraction. We're going to leave the top as x plus 1, but now we need to multiply by the derivative of the bottom. And I'm going to save that for the next step. We'll worry about how to differentiate this square root in the next one. Finally, we're going to take our bottom, our original square root of 2x minus 3, and we're going to square it. Of course, here, the square root basically gets to cancel with the square. So the bottom actually will just be a 2x minus 3. Next, we're going to have to use the chain rule. The chain rule specifically for this derivative that we haven't dealt with yet. Where we want to keep in mind that the square root of 2x minus 3 is really 2x minus 3 to the 1/2 power. And so we're going to use the chain rule, or maybe even we could say that we're using the general power rule. For the fact that this is something to the 1/2 power. We're going to make a few simplifications so we go. We don't need this 1 anymore. I mean, we're just multiplying it by what we already had. The bottom is now just 2x minus 3. But here, this is to the 1/2 power, so we're going to bring down that 1/2. We're going to change our power from a 1/2 to a negative 1/2. Remember there, we're taking the 1/2 minus 1, and we get negative 1/2. But now we need to multiply by the derivative of the inside. The inside here being the 2x minus 3. The derivative of 2x minus 3, hopefully you can see that's a 2. Well, here's one nice thing. This 2 that we have here can actually cancel out that 1/2. So you could say that our derivative is this function here. And in fact, at this point, we could go ahead and just plug in our x value. Plug in this 2, and we get the slope of our curve at that point. The slope of our tangent line. Well, because this kind of simplification does happen a lot in problems like this, when we have like quotients and all that, when we have square roots in the bottom, I'm going to go ahead and simplify this down to something that will look a lot nicer than what this already does. Okay, so we have a little bit more room to work with. We'll move this to another page. I'm going to rewrite this negative 1/2 power as an actual square root. So we saw this here. We have the x plus 1 here. But now this means that we have a 1 over the square root of 2x minus 3. In fact, maybe we should write that with the x plus 1 on top. So we'll have x plus 1 over the square root of 2x minus 3. Now, of course, having fractions inside of fractions is not the best. This really seems really overly complicated at the moment. What I'm going to do in order to simplify this is I'm going to multiply the top and bottom by this square root, so that when I multiply here, it's just going to get rid of the denominator. So I'll have 2x minus 3 multiplied to the top and to the bottom. Well, first of all, when I multiply it to the top, I need to multiply it to each of these two terms. The square root of 2x minus 3 times the square root of 2x minus 3. Hopefully that's pretty clear that that's just going to turn into 2x minus 3. I mean, we are basically squaring that square root. And then over here, the whole point was that those cancel out. So we're just left with the top. Make sure that you don't just write this as minus x plus 1 without the parentheses. That minus is going to have to end up on both those two terms. On the bottom, we have the 2x minus 3 times the square root of 2x minus 3. Notice that this is basically 2x minus 3 to the first power. And then this square root over here is really 2x minus 3 to the 1/2 power. When I combine a power of 1 and a power of 1/2, I get to add my two powers together. 1 plus 1/2 means that I have a new power of 3/2. And then we can go ahead and simplify the numerator. The numerator actually simplifies pretty easily. We have 2x minus x goes to a single x. We have a minus 3 and a minus 1. Remember to distribute that negative. So we have a minus 4. That should be a minus 3. And this is the form that I kind of prefer for this type of derivative. It's definitely the easiest one to work with anytime we want to be applying derivatives to various problems. Especially when we get to chapter 3, this actually you can already read some of the information that we'd like to solve some of those problems just based off what we have written here. But I'm not going to get too much into that right now. But the point here is this is definitely the simplest form. Now, you might say because we have a fractional power here, maybe you don't like it. If you really prefer, you could rewrite this as x minus 4 over the... Don't really need the 2 when I'm taking square roots. We have the square root of 2x minus 3 to the third power. I prefer just using the fractional exponent. That might be because I'm more comfortable with them than some people are. But I find that it looks a little nicer to me. If you prefer one over the other, go ahead and use it. Alright, going back to actually solving the problem they asked for, though, we're going to go ahead and use this derivative to find our slope. Remember, we are wanting to find the slope at the point 2, 3. That was given in the problem. So here we're going to take the derivative at 2, just following their formula from before. We had x, which is now 2, minus 4, over 2 times x, which is now 2, minus 3 to the 3/2 power. course, the top here is a -2. The bottom, this is 4 minus 3, or just 1 to the 3/2 power. I kind of picked one that would make it a little easier for us on the bottom. 1 to any power is just 1. So really our derivative here is -2. This is the slope of our tangent line. And we already have the point. We have the point 2, 3. So we can use the point slope form. Basically, y minus our y value of 3 is equal to our derivative or slope of -2 times x minus our x value of 2. Of course, we like to put this into our slope-intercept form. That's the one that everybody prefers. So I'm going to go ahead and distribute the -2 to both those two terms, and I'm going to move the 3 over. So here we have -2 times x. -2 times -2 is a +4. And then, of course, we're adding 3. So y equals -2x plus 7. And this is something that we can easily check by graphing. Just going to go ahead and graph the original function. F of x was x plus 1 divided by the square root of 2x minus 3. We have this curve here. Notice that we don't have anything over in the negative x values because, well, if you think about the domain of this, it only goes down to 3/2. We can't have any x's less than 3/2 in this domain. But we have this curve here. They claim that we have a point of 2, 3 on it, which GeoGebra called that A. And if we go ahead and graph the line y equals -2x plus 7, it very much actually is tangent to this curve at that point. It really does represent the actual slope of the curve at that point, which is what we wanted. And it really, we should be fairly happy that all of our rules so far have resulted in something that actually does agree with what we expect to have. So, at this point, we have all of our differentiation rules, at least for any of the functions that we've been talking about so far. The only differentiation rules that we'll actually come across after this point are the rules for exponentials and logarithms. And you even can see them on our table of derivatives if you wanted to. From this point forward, we're mostly, at least until the end of Chapter 3, we're going to be talking about various applications and various other things we can do with derivatives, and less about actually how do you take derivatives. So, see you next week, and we'll talk about what we call higher order derivatives. Just taking it one step further. So, see you then.